let's get started. Hi, happy Tuesday. Thank you for coming. Good to see you. So I've got some announcements today that have just kind of piled up since Monday. Um, First up, if you have not set up multi-factor authentication, you should do that as soon as possible. That's due Monday. And that just involves like you go here, you download an app, and then you link your app to your SMC account. And then that way, when you log on to something that's SMC, it'll send something to your phone and you'll just like enter a number and then you're good to go. So make sure that if you haven't done that, you have to do this by Monday. Otherwise, you'll get locked out of things. So make sure that you've done that. That's required of everybody. The other thing is I'm teaching a course in the spring semester, which is mostly geared at like you guys, people who have taken 222. The title is Graphs and Applications. And this course is all about how things connect to each other. So I've got the whole blurb here, but like the idea is there's all these sorts of problems that are not only in computer science, but like everywhere. So there's like traffic lights, there's scheduling for like how can you schedule someone's courses when some two courses may be at the same time. And so like you can't take both of those in the same semester. And so this class is going to look at how can we take these like different problems, abstract them, look at them on a higher level, and then solve the problem. And so this class is designed to be like a bridge between this class 222 and 374, which is data structures and algorithms. So it'll provide more of a background if you're if maybe the math side, the theory side of things isn't as strong. This course is hopefully will strengthen those skills. It's also something that I'm super passionate about, and so I'm really excited to teach this course. If you've taken discrete mathematics, I think math, what was that, 240? I don't remember. But there's a course called discrete mathematics, and if you've taken that, then great, but that's not required. So talk with your advisor. I think they might be mentioning it if it's an option, but I'm looking forward to it. It should be a really cool class. All right, my other announcement is next Wednesday, the tech club is going to have a talk with a tech person event where we're bringing in someone who works in the industry. It's on Zoom, or he's coming in on Zoom because he lives in Arizona. And yeah, so he's going to talk about what it's like to be in the tech industry. And he's working at American Express. He's also worked with like AI stuff. So you can ask him questions about that. And it should be good. So that's next Wednesday, 5 to 7 p.m. In Galileo 114, probably. Okay, those are my big things happening announcements. For more class things, homework 1 is graded. So those grades should all be posted. If you did not get a good grade or you want to improve your project, you may resubmit it. There will be a cutoff deadline, which I will announce in the future. But if you want to keep working on it and resubmit it to try and get 100%, feel free. I've written comments in the assignment, so you should be able to see here's what you got wrong. You can also always come to office hours and talk with me, and I can help you out. In terms of the statistics, the highest a group scored was 98, lowest group scored was 26, or 0 if you didn't submit it. Overall, I think you guys did a really good job on this. It's a hard assignment. Um, It was great.
Yeah.
It was great.
We
Yeah.
had some like issues where we thought it might have been like you might not appreciate artistry involved, but the art.
Yeah, all the heists were really creative. So good job, everybody. You did a really good job. Say that again. So that was good too. That was great too. Yeah, I think so. Yeah. Maybe we'll have a day. Maybe we'll have a day in the future where you get up and show it off. Maybe we'll have like a presentation day in the future. Okay, so some common errors for the homework are if chances are you got points off for binary array, it's probably because of the field. So for binary array, the idea was that you have a field that's a Boolean variable and not a char array or a string. So Boolean array, that's what I'm looking for. The number one thing for the heist was that you didn't include the script. And the other thing with the heist tended to be just like error handling. Like if I put in something wild and out there and you didn't account for that, then I probably wrote in comments, here's what went wrong. As always, if you have questions or concerns, come talk to me and I'm happy to discuss and figure out a way we can go forward. Lab 6, sorry, question?
So we can fix it?
Yes. Yeah. So feel free to fix it, resubmit. Yeah.
They show you how to do this two-step, whatever, Microsoft.
Hold on. Let me pull that up. Well, that's unfortunate. Let's see. So what I did, I followed the instruction guide.
It says like I've tried this QR code and it's invalid, yes, like recreate a new QR code.
Oh, that's unfortunate. I would ignore the QR code and go to like the IT website if the QR code's not working. Like go to the you can't log into stuff. Right. Like you need to be able to log into stuff, so you've got to do this. Okay. Okay, my last announcement. Sorry, there's a lot of announcements today. 1 and 2 are available for the new labs. So if you want some extra credit, you can do them and then submit to the feedback form. They're in the original like lab assignments. So lab 1, let me pull that up. Let's go down to lab 1. So lab 1's got a redo link and a feedback form. If you do it and fill out the feedback form, then you email me and said I filled out the feedback form, then I'll give you 5 points extra credit. If you want to replace the grade that you have, then just submit the zip file and I'll grade it according to this new lab and it'll just replace your grade. And then if you fill out the feedback form, I'll give you 5 points extra credit. So lab and 1 and 2 those are ready to go. I'm working on lab 2.5. I've split lab 2 into arrays and strings and scanners. So the arrays and strings part, that's all ready to go. Scanners is coming probably by the end of the week. This can help you if you're still feeling confused about some stuff in Java. I recommend doing the labs and it can help remind you I've improved the instructions And so hopefully it helps you understand better. The other thing for the labs, they're written for Eclipse, which is another kind of IDE. We're using VS Code. You can do it in VS Code if you want. That's up to you. Okay. Any questions, comments, concerns, other announcements? Cool. Okay, so let's review the stacks. Did I open that? No, I did not. There we go. Okay, so last time we started looking at stacks and queues, and these are two really fundamental data structures that help us do all sorts of other things in problem solving. So we use these when solving problems.
Is that actually inside of a Pringles can?
No, unfortunately. I Googled inside of Pringles can, and this is someone else came up with this. I think this stuff at the bottom is not actually there, but like the upper half, like, yeah, that's probably what
Oh, it's actually that full. Pringles, I feel like only put a half empty.
So maybe this part is like, if you remove that, then it's an accurate inside of a Pringles can. But yeah, so a stack is like a Pringles can, this data structure that holds objects. So if our objects are Pringles, then the Pringles can is a stack containing Pringles. And so the way that we look at a stack is we'll draw it with this sort of structure where we've got two walls on the side. It's got a bottom, but the top of it is open. So we can like reach in, grab something, take it out. Or if we're putting something in, we can just plop it on top. So that's a stack. It's a really simple structure. And we have 2 to 3 major operations, one of which is push to add things onto the stack. Another is pop, where we take something off of the stack. Another is peek, where we just see what's on top of the stack. So yeah, so a stack is a first in, last out sort of data structure. So last time we looked at 2 major implementations of a stack. So first what we did is we made an interface, which says anytime someone makes a class that is going to be a stack, I want it to have these methods. So let's go over there and look at stack.java. And stack is an interface. We've parameterized it to say this stack is going to hold something of type T. We don't know what it is. We could know what it is right now, or it could be some class that someone creates 10 years in the future. It could be anything. So we parameterize it and just say T. Let's just call it T. And the 3 methods, so our interface is our method contract. And we've said anything that makes a stack, I want it to be able to push. I want a method called push. And I want a method called pop and a method called peek. Those are our main methods that we want a stack to be able to do something with. So with that, we made 2 different classes. We made AL stack, which implements the stack using an array list. And we made LL stack, which implements the class using a linked list. So 2 ways of creating this stack. So we've got our kind of abstract idea of a stack from these drawings. Like this is the sort of thing that we want a stack to be able to do. And then the question is, how do we write that in code? And so we have 2 ways of doing that. So I think we went through the AL stack last time. So let's go through the LL stack. So I think, I think we got everything except peek. In this code, right? We've got insert. And the thing with these classes is we're not doing a whole lot of work. We're mostly just leaving the work to the data structure that's sort of underlying, that's storing all the data. So in LLStack, the linked list is storing the data, and we're just using the methods and giving them a different name. So does someone want to pull up their code and tell me what peak should return? Or you can look at pop and tell me. Yeah. Yeah, great. That's it. Because for peak, we only want to look at the thing that's at the top of the stack and return that value, but we don't want to change the stack in any way. Okay. So I think that's good for stacks for now. Let's see. So I have an activity for stacks, but I think I'm going to leave it for I'm going to leave it for next time. I'm going to put it into a lab, and then we'll work on the lab next time. That's my plan. Today let's talk about queues, do the same thing. We'll do array list and linked list. Linked list might take us a bit more time because it's a little bit different. Okay, so for queues, we'll draw some pictures to start. So who here has been in a line at a grocery store? Great. You know what a queue is. So a queue, we tend to represent it as like we've got these two horizontal lines, and there's things in the line. So like if it's people at the grocery store, you can draw stick figures. And so with a queue, there's still a notion of like you can't cut in line. So like doing this is not recommended or not supported. But with a queue, we've got the front and the back, which makes sense. Like if you're in line at the grocery store, the person in the front of the line is ready to have all their items checked out. The person in the back of the line just joined and now they're waiting, right? And so sometimes we'll draw it with arrows, like the arrow going into the queue, that's the back, because someone's going to join the line, and the person at the front of the queue, that's the next person in line. The other thing with a queue is usually when someone, so like, let's say this is the teller, when it's time for someone to be served, they will be removed from the queue and then served. So we're not serving the person in the front of the line. They get out of line, they get removed from the line and then served. So like first we need to remove them, and then they're ready to buy all their groceries. So that's a bit of a key point. In terms of what we call these operations, it's really similar to a stack where there's only 2 or 3 operations that we really care about. We've got enqueue, which means to add to the line. So it adds to the back of the queue. All of these letters matter, unfortunately. And then we've got dequeue, which means we remove someone from the queue. From there, we could also implement like peak if we wanted to, but enqueue and dequeue, those are really the major operations that we're working with. Okay, let's see. What did I miss? So yeah, so this sort of data structure, so stacks were last in, first out, or first in, last out. The first thing you put in, everything else piles on top of it. And then once you take all of those things off, then the first thing you put in gets to be the last thing that comes out. But with the line at the grocery store, if you're first in line, you're the first person who gets served. So it's first in, first out, FIFO. Yeah, so we've got two operations, NQ and DQ. I will note that, let me write it out. DEQUE differs from DEQUEUE. So this is pronounced deck, and that's something different. So spelling DQ like this is required. We have to have all those UEs in there. So this is pronounced DQ, and this is pronounced NQ or on Q, or. But the difference is like Q and not, this is deck. So yeah, so with a queue, so we've got two things to keep track of, as opposed to with a stack. We have a stack, there's only one thing we have to keep track of, which is the top. For a queue, we have two things, front and back. So what I would like you to do is in your groups, I've got markers today. I want you to go to the board and draw pictures. So we're going to do the same thing. We're going to use like an array list. So if you draw like a big long rectangle split into stuff, what's the front of the queue look like when we're putting the data into an array list? What does it look like when we're using linked lists? So let's start with array list. Draw pictures, and then we'll come back together and write some code. But I want you to think conceptually about this for a second. So if this is the sort of structure that we want to implement, what's the front of the queue? What's the back of the queue? What does NQing and DQing like if we're storing this data in an array list? Okay, I'll grab my markers, get in groups, go to the board. That's not my markers. These are my markers.
Yeah, let's go. Thank you. Oh my God, you have the market call. That's like some budget. That's fine. It's still, on the server. Like,
That's not good.
No.
It's-
You guys get like so loud and all.
Wait,
I realize I can hear everything. Getting out of now. Yes. Big reputation. You guys need a voice train next time. You guys really want I told you. Yes. What did he say? The voice small. Not that I'm aware of. What did he say that was like reverse? You're like live. That's what we talking about. I was telling him over you guys still like. What did he say? Really here. You were talking about something. You were talking about something. Say. Like every time I'm not. Well, low-key, I was a psychologist. Oh, are we running like masturbation is like challenging to do something.
Sure. We're just like, right, your short sentence.
You hug weird. I saw you around. No, you just see her.
Hi, let's keep the conversation.
attack. That's it. I'll draw the other list. Wait, do I draw a real list weird or no? We're literally like doing that. Slaying is the public, I think slaying is the public forum. It's like back in the day. Like, you know what they say when I'm on. Like, I'm sure you said. What? But it was we did. Maybe start. Maybe start. You know, you're always in one. I'm guessing.
It's like.
Right. Why is it DQing? Like, remove that. And then go with like, entering. Go 0. Hi. We're at 0. Oh, Pete, that's just like.
And then once you're done, also do.
0, right?
Okay,
0.
so maybe.
Inserting? In the middle? Is that what you
Yeah, the very first.
And
I think so.
I'm guessing it's like the.
You could name it like that.
Okay, now we're gonna add.
Yeah. I'm super.
What are we doing?
You want to be able to, I get to go to their home number, removing and.
Yeah, let's do.
And Q, DQ. You guys need to see how it's going next. It was like this.
Wait,
That's the most girly dog I've ever seen. I mean, I slandered in my own real dog. You slandered me.
okay, what's the front of the queue?
0. The back was 10. Right? Is this wrong? Is it wrong? Is it wrong?
So then how do you remove something from the front? What's, if we're using a rail, what method do we have?
Oh, no, the front DQ.
So method, if we're right at, what do we, what rail method do we follow to make that happen?
Remove something and just. Off the first one.
Google a rail method.
Well, you have to know the size. Exactly. And if this might be.
Yeah.
Learning process.
Pretty about the size.
And then. Yeah, we're gonna do the Q. Dot remove.
You gotta- I don't know.
Okay. 0. Yeah, that's on. Okay.
What about?
Which to do.
Yeah.
Oh, the add something. That's adding.
Yeah, I want to add.
Specialist. There's so much more catching up. Yeah, that's the beauty of collaboration. You just ask. You got. Next 30 callers next week.
So what's and what does
Okay. The end. Oh, and adding. Something to the back.
how do we do that? With an array? Yeah, what's the method for locking in a array list?
Hey, I got. Oh, okay. Okay. Yeah, not.
Yeah, yeah.
Oh, okay. Yeah.
So can ask the question again, and the way you represented it.
I do it. That's.
We added it.
Oh, bro, you.
Not,
No, you literally like goes Okay.
the array list method.
You go do that. What are you gonna ask about motion now?
Alright, Lakeland.
Let me see. Wait, so I don't know what the standard how you proceed with the Java. If you don't use Hugging Face. Next time, I'll check the documentation. Make sure it's not here. Send out the last one. Explain this. Is that just a random mouse from like one of these?
Yeah. Is that necessary?
I don't think so, bro. Called you out. This is my. And then just adds it's on sitting. God, he's an expert on this. So much better. Well, next time you gotta record it, so you have a minute to next time. Like next time you see me, I'm pretty sure that. You're sure about it. Just like filming. You're sure about this is huge. Kind of guy who can like.
Yeah.
Me?
Yeah.
The same stuff. Me? What?
So if you have.
A radio small. Like then after you for certain charges.
Got an entail.
Just like you said, if I said something, you like hella salty, so you say you're.
Yeah.
It is.
We'll talk about that.
Yeah. It is.
Not a problem.
Parentheses.
It is still not.
I think my problem makes consider. Yes. I feel.
Okay, let's go back and talk about it. All right. Thank you for your participation. Yeah, so let's come back. Let's write our queue. We're gonna make a queue interface, and then we'll do array list queue, and then linked list queue. And maybe we'll play around with linked lists. Okay, I'm gonna make a new package. I'll call it queues. And then a new file. But no, come back. Queue.java. And this is going to be an interface. So just like before with the stack, we have, here's my method contracts. Here's methods that I want every stack to implement. So, or not, yeah, for this we're doing queues. So our main methods are public. Let's do enqueue first. So, because we're just adding something, so we don't need to return anything. And so this will also be parameterized, right? Because this queue is going to hold items of some type. We just don't know what it is yet. So we want to be able to enqueue something to the queue. And we also want to be able to remove something from the queue. To say, so remove it and return it. That's the other important part. So don't forget, we also have to return the thing that gets removed. In terms of peek, I think peek, so like enqueue and dequeue are the basic ones. If we want to add peek, we can maybe add it to both ends to say like peek at the front and peek at the back to just look at the things and return them. But that's that's fairly straightforward. Okay. give you a second to get all that done. All right, are we good? No? Few more seconds. Okay, how about now?
Give it 12 seconds. I'm good. 12 seconds.
Great. Okay, so let's make our ALQ.java where we're going to implement a queue using the ArrayList data structure. So we're also going to parameterize this class because we're going to store something in it. And what's our field for this? ArrayList, yeah. So I don't know. Okay, I'll import that. No.
Sorry, it's like not going down. Yeah, like this thing's like, oh, I don't know. You know, the computer acting up, the phone acting up. My technology's not working well today. You know,
Oh, I reloaded it to see if maybe because ArrayList didn't want to import.
Jesus, yeah. Dude, this is my hardest class I haven't taken.
Oh, import, there we go.
Yeah. Yeah.
Okay, hi, can we talk about computer science, please? Thank you. Okay. Actually, so for the constructor, I always forget. So we just declare the field. We don't actually initialize it to anything. Because we want to initialize it in the constructor.
Right.
So we just want to declare it as a field to just say, this is the name of my field and here's what type it is. And then in the constructor, when we create an ALQ object, we actually initialize the list. Okay. I have forgotten to say implements queue. So when I say implement queue, there's two options. There's queue that I wrote and queue from Java util. I want to use the one that I wrote. Okay, so now I've got errors saying you don't have the abstract methods from the interface. So let's add them. Okay, so what's the question?
I like look down for 1 second, I look up and was
That's because I added it was automatic. It added all the methods from the interface. So if the ALQ's got a red squiggly line, you hover over it and go quick fix, and then add unimplemented methods, and then these all pop up.
If I spelled Q correctly, I think that's my issue.
That might be it. So I think Q also needs to be parameterized.
Okay.
Q, U, E, U, E.
Q, U, E, U, E. Dude, I'm not able to like extract
all the interface fields from like the array list queue. Like where you did the
Public interface queue. Can you go back to the queue? Queue. Use an interface. Yeah.
Right, and we just made that.
And then, so if array list queue, I just can't initialize my own queue, like in the array list queue.
No, wait, wrong method. Okay, so,
Line 9.
okay, let me come over there really quick.
Oh, wait.
So yeah, so the goal, so, okay, so if you've got it working, go ahead and implement it based on what you do on the board. And then I'll keep hot for it as you go. See, take this. So that's because it's not in like a project.
No, it's not. Oh, yeah, it's just an online.
Yeah. So it's like
You
a-
don't need the back.
I'll go over it and they'll do that. There you go.
That's okay, I'm just looking at you.
So this needs to go in a constructor. So we've got public ALQ parentheses and that, so just
Oh,
that,
this is in
that
different-
second line goes in the constructor.
So, but all the overridden methods go in the system, it's the constructor.
So all those methods are outside the constructor. Don't we make it bigger?
No, I think it's one. Okay.
Yeah. Outside the parentheses,
Detail.
okay, delete the parentheses.
I hate the
Type of
way the word
parentheses
queue is
for-
back. It's so weird. It's terrible language. I use one, just like
Minus
stare at it,
press
like,
L.
this is right. Just that you just.
This one hasn't colored.
You have QT,
Like, you could have left that.
Q.
That was patriotic.
so save that file,
You know, patriotic.
yeah,
Big artist,
save it as
makes house music.
Q,
Playing.
capital Q U E E.
Hmm? No, you gonna sleep? Where you go? Huh? You went, huh? Yeah, I was not. Scary.
Yeah.
I originally heard it as like lowercase q's and then
Oh, yeah.
extensions.
And
now, like, when I look at this,
Then you're leaving, then you can go further. Yeah, the rip off.
no,
It was the cool city. Such as mine.
they renamed the files.
Who's the artist that was here?
Magic B and.
Yeah. Martin Hayes.
You.
Go back to the interface. All right, are we good? Okay, so we're storing this information in our array list. Let's just talk really briefly. What should the front of the queue be? Is it the beginning or the end of the array?
Beginning.
We've got to vote for the beginning. Does anyone have something different? I think these guys have something different over here. So I see two where the front of the queue is at the end. So let's think about this. Why would we want one or the other? Let's think about it in terms of no, actually, let's talk about this. Let's talk about this with linked list. I think the efficiency is easier to look at when we're talking about linked lists. So let's save the why for this for later. Let's just do a show of hands. Who votes that we should have the front of the queue at the beginning of the array list? Okay, cool. Simple majority. So the back of the queue is at the end of the list. Front of the queue, beginning of the list, back of the queue, end of the list. If you've got yours different, then your methods will look a little bit different. That's just a decision that you as the programmer go in and you're like, I'm going to have the queue at the beginning, or the front of the queue at the beginning, or I'm going to have the front of the queue at the end. That's a decision you make, and then you just need to make the appropriate changes. So either one works. Okay, so if we are adding to the end of the array, if we're enqueuing to the end of the array, what ArrayList method should we call? Yeah.
You don't have lots there.
Yeah, that works. Also works is q dot. Nope. I think this happened. I think just add. I think it does the same thing. So add last or add equivalent. Okay, for dequeue, what do we need? If we are removing from the front of the queue, so the beginning of the array, what do we need to say for dequeue? Yeah. Yeah, probably. So we can ask the queue if it's empty, and then yeah, what did we use for last time? Index out of bounds? No, we did. Did we do anything? I don't think we did anything. Yeah, we should definitely have something. Say that again. Illegal state? Maybe. I think that makes sense. You can make an argument for that. Zero. So you have the back of the right, but no, so for your drawing, it would be remove zero because you want to remove the first thing in the list. To dequeue, yes. Yeah. So in our implementation, we've decided, no, wait.
Yeah, we haven't said something.
Yeah, front and beginning. Sorry, I got confused. You're correct. Yeah. The front is the beginning of the list. The back is the end of the list. You're correct. Okay, so for peak front, We probably also want these exceptions. I'll just copy them over. Also for peek back. What do we need to? Yeah, it's just get, and then front is index 0. So return q dot get 0. Or I think get first also works. Yes. And then for peek back, there's get first. We could say get last. An equivalent is get for size minus 1. Equivalent does the same thing. Okay, sounds good. Cool. So that's our array list queue. So again, it's a relatively simple data structure, but it allows us to do some pretty complicated things. Let's look at linked list, and then we'll see where we are in time. We might have a little discussion. So for a linked list, let's actually talk about it first. So if we've got a list, this is how we've been talking about linked lists so far, right? Where we've got one pointer, the head, that holds the front of the list, or the head of the list, the front of the list. So there's two options for how we can orient this, right? We can have this be the front of the queue, and this will be the back of the queue, or vice versa. So let's say, okay, we're gonna do a thought experiment. We're gonna do this way, and then we're gonna flip front and back, and we're gonna ask which is better. Okay. So first, so for NQ, we're adding something to the back. We know how to do that, right? So adding something to the back, NQUEUE is like appending, adding something to the back of the list. We know how to do that. What's involved in adding something to the back of our singly linked list? Bingo. Yeah, so in order to add through the back, we need to go through until we're like right before where we want to insert, and then we have to add that new node after that, right? So we have to traverse. So the thing with traversal is this is where we start getting into efficiency, where once we're done with, I think, this and maybe recursion. I forget how the order is. But we're going to talk about efficiency. And so if we've got a list of 5 things, then we just have to go through 5 things till we get to the end of the list. Not a big deal, right? But if we've got a list of 100, 1,000, 10,000, then it starts to like that work to just go through every node till we get to the end, that work becomes greater. And so the goal as programmers is not only how do we do it, the goal when we're writing an algorithm like this is to say, how good is it? Like, is this the best we can do? Can we do better? Can we do less work while still accomplishing the same goal? That's what we're trying to answer with this thought experiment. And so we say this, so like, I'm going to give you a sneak peek. We use something called Big O in order to measure how good some bit of code that we're writing is, so how efficient it is. Big O is the worst case complexity. So we tend to generalize it as like if the thing that we're working with, if the size of our data is n, we'll just like give it a variable n, then if the size of our input is n, how many steps is it going to take to get to what we want to do? And so in this case, when we're adding to the back, if the back is at the end of the linked list, this is going to be O of n because we have to traverse. There's an operation that's going to happen n times. We're going to go all the way to the end of the list. And then, so that's O of n for NQ. For DQ, it's just removing the thing at the head of the list, right? So we're just like taking the thing at the front of the list, removing it. Do we need to traverse through the list at all? No, right? Because it would just be removing the head. No traversal required. And so this we say is big O of 1, which is as good as it gets. So yeah, so in this setup, DQing is quick, NQing is not as quick. That makes sense so far? Okay, now let's swap. So we're going to have this is, okay, so the head was the front. So now this is the head and this is the back. So we're switching mindsets. And the end of the list is the front of the queue. So again, let's do NQ. And what's involved in NQing to the list? Just like adding a new head, right? Yeah. So that's insert 0. So is there any traversal involved in that? Nope. Any other operations that maybe we care about? Do we have to remove back? Yeah, so it's just reassigning the head. So I would say that could be a trivial operation. So I would say this is big O of 1. So again, constant time. It doesn't rely on the size of our data at all. So it doesn't rely on the size of the list. For DQ, what's involved with DQing? Removing from the front. That's what we're trying to do. So the front of our queue is the end of our list. No, so in this scenario, the front of the queue is at the end of the list. So how do we remove from the end of the list? Right. And so what's involved in the dot remove? Right. We still have to traverse to get all the way. Traverse and then remove last. So this ends up being remove size -1. That's what we would call for this situation. So between the two of these, first of all, this is what O of I would say O of n because it involves traversing. Okay, so between the two of these, is there any benefit to one over the other? No? No, right? Because like we can, so in terms of benefit, if we're looking at efficiency, we've got constant time or linear time. And then we've got constant time or linear time. Same options for both of them. So one is not immediately preferable over the other. The only thing that I would say would make more sense, like logically, is this, just because like the head of the list is the front of the queue, the back of the list is the end, or the end of the list is the back of the queue. So that might just make more sense like logically in our minds. But as of the way we've set it up right now, that's kind of the only benefit. Okay. So how could we fix this? What's something that what do you think? How could this be improved? So the main thing is we don't want it to have to traverse the list in order to find the back. How can we get around that? Yeah. Yeah, so maybe we have that's supposed to be an L. So like if we've got the head, maybe we want the tail. Maybe we want to have like a tail pointer. But so there's an issue with that is if we've got a tail pointer here, if we actually I think that might work. Right, because if we add something, then we say tail doesn't point here, it points to the next. And because we have next pointer, that's allowed, right? Because we can go forward in the list. The issue here is, and this may be why we really don't want to use this version. If we had a pointer here for where we're in like the back of the list is the back of the queue is the head of the list. If we had a tail here, if we were to dequeue here, so like cross that off, we want to move tail over here. What's the problem with that? Right, we can't go back. The links only go one way. So if we were going to implement it like this, then I would say we would change, it would probably be smarter to change the list from a singly linked list to a doubly linked list. If we wanted to set it up this way, then if we have links going both ways, then we can move tail backwards easy as pie. Like that's not a problem if we've got links going both ways. But if the link is only going one way, then to reassign the tail, we would have to start at the beginning, go all the way through. Okay, now here's the tail. Does that make sense? Okay, so I think we've landed on front and back. Front is at the head, back is at the tail. And then tail, we can just reassign to always be the back of the list. All right, sounds good? Cool. Let's make it happen. Okay, let's make a new file. llq.java. So I'm going to have LLQ and it implements my queue interface just like before, so I don't have to reinvent the wheel for my method names. And then I'll add all these unimplemented methods and I'll let it sit for a second. Take attendance while I do that. All right. Are we good? Anyone have issues? Okay. What's our field? So, okay, here's the question. Do we want to, so the way that we've drawn this picture, we have like an additional requirement that is imposed upon a linked list, right? We've like added this tail element. So first, let's go back to LL and maybe add that in. So that's one option, is to modify LL. The other option is to like, so we could just take like the add to back as is. But let's modify LL to say we want this additional functionality. Okay, so to do this, so we've got a field head and size. And so to add a tail, let's just have another field. And then we just have to go through and make sure like this dot head is null, this dot tail is null. Oof, I did not think this through. Okay, this might be this might be more than I bargained for. Let's make a method that calculates the tail. So the problem is, so this constructor is taking in some previous node. The node may have things after it. So, and so that's why I've got like get size to actually go through the list and count how many things come after this node. So to calculate the tail, the idea is I just traverse the list, and then when I find the last thing, I mark it, say this is the tail. So it shouldn't be too difficult. So I'll have a pointer called temp, and I set it to start at the head, and then I'll say while temp is not null. Yeah, while temp is not null, then I need to iterate it through the list, so I'll have temp equals temp dot get next. And then what's my condition? If something, then tail equals temp. So I want to set temp tail as the last thing in the list. So what's the condition for that? If I'm iterating through the list, at what point do I know that temp is the last thing in the list? When temp equals null? Temp.get next. So when the thing right after temp is null, then temp is at the last point in the list. So if, let's say, there's other things before it, this is temp, and there's nothing after it, this is the last thing in the list. So if temp.get next is null, then tail is temp. Then I can just return. Am I returning? Actually, since I've set it up to return. Okay, so since I've set it up to return a node, I'll say return temp if we're at the last thing. I think the only other case would be if the list itself is null. So like if I was given a null node here, in which case temp would just be null, the tail would just be null, which is fine. Okay, so that makes sure that when we are creating a list, we're setting up the tail correctly. Get node. I think so. Node equal. Why do I have that? I don't know. I think for this one, we can just add another condition. So this case, the code that we've got here, that is going through the list to find the ith node. But we can add a condition to say if the index is equal to the size minus 1, then just return tail. If index is equal to size minus 1, then return tail. Okay. So I think that method's good. Is empty. Maybe also add if the head is null and the tail is null. For make empty, we'll say this dot head equals this dot tail equals null. Get size, I don't think we need to change anything to that. To string, I don't think we need to change that. Find, that starts at the head, I don't think we need to change that. For insert, so since we've made the change to get node, do we need to change anything for insert? So in get node, if we say, if you've given me the size minus 1, then I just give you the tail. So I think insert can remain as is. And then similarly for delete, I think it can remain as is. Okay, so I think that should be okay. So what were the changes that we made? We said, we made make empty, make the tail also null. For is empty, we added check that the tail is null. For get node, I think this is the important part. We said, if you've given me an index that's equal to the capacity, so size -1, then just return the tail. We added a brief method just for setting up the list. And then we have added things to the two constructors. So to calculate the tail and initialize the tail. So those are the changes that we made to LL in order to be able to do things with our LLQ. Sounds good so far? Okay. So now that we've got that, what's our field for our LLQ? What's holding the data? Linked list, yeah. So we'll just declare that. I'm going to import that type. And then we'll have a constructor where we just say Q equals new LL. Where we will initialize our linked list so that we can then go in and store stuff. Okay, what's our NQ look like? If yeah. Okay, so if this is what we're looking for, and we NQ to the back, what's the method that we need? So let's go back to LL. We've got size, get size, toString, find, insert, delete. Insert. Insert where? It's 0 or size -1. If we're adding to the back. Size -1. Oh, and we need to give it the data. For the DQ, we'll probably also need what? This is part of our boundary cases, our error handling. What could possibly go wrong? Yeah, so if there's nothing here, so if Q dot is empty, then I don't know, legal access error, maybe a legal argument exception. I don't know. We'll say, hey, the queue's empty. You can't do that. So once we've handled that, what do we do? So our two options are insert or delete. Delete, right? Because we're removing something. Queue dot delete. What index are we deleting? Zero? Yeah, because the front of the queue is the front of the list. So we're just deleting the thing at the front. In LL, we said that delete has a return type of void. So we need to add an extra step to this. So we need to actually like get the data. So what do we use for that? I think just dot get, right? Insert, find, get node. Do we have get? We do. Okay. Would help if I put the semicolons in the right place. So first we need to save the thing that's at the front of the list. And then we delete it from the list and then we return that. So returning, we have to remember to do that. Okay, so then for peak front, that's just this, right? The thing at the front is just at index 0. So we can just return the thing at index 0. And for peek back, we return the thing at index size, yeah. That'll be q dot size -1. Cool. Great. I think we did it. Okay. All right, so let's talk a little bit about what we use them for. So we'll yeah, okay. So I'll have the activity next time we'll have like that'll be lab, was it 7 now? 7. So there's ways that we can like extend this. So queues and stacks as it is, fairly simple. Queues, there's things that we can do to extend the functionality. So if we wanted to, we can have like wraparound where we have some sort of circular array and it can like it goes back to the beginning. So in that way we could have like sort of this sort of thing where maybe this is the front, this is the back. There's all sorts of ways we can do it. We can also extend this to be a deck, which is a double-ended queue, which is instead of just the back and the front, where we add to the back and remove from the front, we could also maybe add to the front, remove from the back. So that's possible too. So for this, I think we would probably want to have a doubly linked list. Because if you're going in multiple directions at the two ends of the list, then it probably makes sense to actually move it forward to a doubly linked list. Other variations for queues, at least, are one of the really important ones is a priority queue, where this sort of thing happens like on your computer all the time, where there are things that your operating system needs to do. Like it needs to move the clock forward, it needs to retrieve something from memory. And there are things that need to happen like every, I don't know, every 5 seconds, every 10 seconds, something like that, where there are some things that are like really, really super important that if this thing doesn't happen, then your computer crashes. And so there are things that certain elements can have priority and should be dequeued before other things, or you can have some other structure to your priority queue. And so this, like it depends on what sort of thing you're trying to model of what that priority actually looks like. Because in the basic queue, it's just first come, first serve. And so depending on how you want to implement the priority, it can look different. So I'll try and have an example about that for next time. The other thing for just sort of in how we use them, you've been working with Stack the whole time that you've been coding in Java, and in fact, other programming languages too. So if you write something and it crashes, then, so let's actually try something. So let me add a main, and then I'm going to say LLQ. I'm going to give it integers. And I'm going to say dequeue. So there's nothing in this queue, but I'm going to try to dequeue it because I want to show you the call stack. So if I run this, I get this, like the standard error message. This is actually a stack where the first thing in this list is, here's the exception. Here's what it says. It says the queue is empty. That's something that we wrote. But then it's a call stack of what we call activation records. So whenever you reach a point in your code where it calls something, it adds that to the stack. So like if you call a method, that gets added to the stack. And then if that method calls a method, the new method gets added to the stack. So we ran the main method, that got added to the stack. And then we called the dequeue method, that gets added to the stack. The idea for a successful program is when a method finishes, it gets popped off the stack. So when a method is done, it gets popped. And the goal is at the end of the program, the stack is empty. So like, let's say we've got our some program. First we call main, and then we call function 1, then we call, and that calls function 2. Let's say function 2 finishes, we pop that off. Function 1 finishes, we pop that off. And then we call function 3. That does something, that finishes, we pop that off the stack, and then main is done. So this is like main calls function 1 and function 3. And let's say function 1 calls function 2. And then function 3 just does something independently. So this is kind of what our methods look like. And this is what our call stack is. So first main gets added, then 1, then 2. Those pop off, and then we add 3. That finishes, gets popped off, and then main finishes, and so we're done with it. The goal is an empty stack at the end. If something goes wrong in the process, so let's say something happened in function 2, then we would stop execution and we give the user, here's the call stack. Here's what the remainder of the call stack is. So something went wrong. I don't know what it is. Here's the state of the program. And so that's what we're working with here, where we say there's a dequeue method in the call stack and there's main in the call stack. So that means at the top of the stack is the most recently called thing. And so that means something went wrong in dequeue, which we know because we added an exception in dequeue to say, if the list is empty, then throw an exception. So we've been working with the call stack this whole time. We've been working with stacks. Now we actually know what's going on. Stacks are also used if you're interested in like computer networks and how the internet works. There's this thing called the OSI stack, where there's different layers for how we are looking at the different aspects of the internet, where there's the application layer, like the transport layer, all the way down to like the physical layer. And the way that the protocol works is it starts at the top layer and it goes all the way down to the bottom. And then that's where the physical like data is sent. And then we go back up to the top to application where the user, like the other person, receives the information. For queues, like I mentioned, for operating systems, scheduling things is really important. For every so often, a refresh needs to happen, or I need to read this thing from memory. So scheduling is really important for operating systems. This is an example of queues where like, if I do a bunch of things, wait, I always get confused when you do this. Okay, so for sure, like, if you ever use like a really old printer and it's really, really slow and you send like 1 million documents for it to print, the first thing that it's gonna print is the first thing that you sent it. And then it's gonna have to go through all of the things until it gets to the most recent thing, and that's the last thing that gets printed, right? For back buttons, undo or back buttons, so let's say I make, like, let's say I type A, B, C, D. If I undo it, first if I undo something, is that a stack or a queue? Yeah, I think it's a stack. Right, so like, because last in, first out. So if I type A first and then B and then C and then D, and then I hit undo, it would be D first that gets undone. And then C, then B, then A. What about back buttons? Is that also a stack or is that a queue? Like the back button on your browser. Like if I go to page X and then I click on a link to page Y and then a link to page Z. And then I click, so let's say I'm on Z and I click back. It should go to Y. So do we represent that as a stack or as a queue? Who votes for stack? Ellie, okay, maybe three hesitant votes for stack. Who votes for Q? Okay, we got 3 minutes. Let's talk about it. Someone who voted for Q, why?
Think in my head, it's just like, you can go so many times. So it's not just like, you're limited to where you're going. So I feel like it has to hold you to in order for you to go back.
Mhm.
Okay, wait, but then we went back and forth. I don't.
Yeah, okay. Hold on. Let me add a new slide here. 2 minutes. Okay, so let's say we visit page X. Let's add X to the queue. Then we visit page Y. We add Y to the queue. And then we visit page Z. We add Z to the queue. And then we hit back. Yeah, I think it might be a stack. I think it might be a stack. So if we visit X first, and then Y, and then Z, then when we're on Z, and then we hit back, then the top of the stack is Y. Because the idea is we want to go back like that in the reverse order, like the last in, first out. Right? So the last thing that went in, so if we're on Z, the last thing that went in is Y. Which makes sense for when we hit the back button. So yeah, I think both of these. Wait, no, where did my pen go? I think that's also a stack. Okay, thanks for coming. I'll see you on Thursday. We'll have some activities to do with stacks and queues. Resubmit homework 1 if you want to get points back. Come talk to me if you've got questions. See you next time. Active learning, great question. Thank you. I forgot. Please turn in ALQ for today. Thanks. Hold on just a second. Let me add that to the side. Thank you.